we've seen that there are four basic gas properties: pressure, volume, moles, and temperature in Kelvin. And if you know those four, you can pretty well characterize a sample of a gas. The temperature has got to be in kelvins. Now, there is a master equation that relates these four properties. And since you have this, once you have this equation, all you have to know are three of these four, and you can calculate the fourth one. Here's the equation. P times V equals N times R times T. This is called the ideal gas law. Sometimes called the ideal gas equation of state. Remember in an earlier video we said that you've specified the state of a gas if you've given someone what the pressure, volume, moles, and temperature are. So that's why it's called an equation of state. This R is something new. This is a constant called the ideal gas law constant. And it can have values that change depending on what units you're using for your pressure and your volume. If your pressure and your volume units are pascals and your volume units are cubic meters, the value of R is going to be 8.314 Pascal meters cubed per mole Kelvin. Those units are kind of important because they tell you what pressure and what volume units that you need to use in the rest of the equation for it to be compatible with this value. Now sometimes if you take a Pascal times a cubic meter, that happens to be equal to a joule. So sometimes people will write this unit as joules per mole Kelvin rather than pascals times meters cubed per mole Kelvin. So you can see it either way. You don't have to memorize this constant, but you do have to learn to look at the units that are given with the constant because they tell you what unit conversions you're going to need to do for your pressure and for your volume. Suppose you wanted to use, instead of pascals, you wanted to use atmospheres for your pressure, and you wanted to use liters for your volume. There is another value of R that you can use. If you use this value, you've got to use liters for your volume and atmospheres for your pressure. Now, there is a problem on your worksheet that just gives you three of these and asks for the fourth one. And that's a very common type of problem that you'll see with this. And it is pretty much just a plug and chug operation. All you've got to do is plug the numbers in. For example, suppose I have a flask and it contains 1.00 grams of gas. And there's like a little foil cap on top of this. I'll tell you why in the next worksheet. We'll go back to this same flask. It is a volume of 259 milliliters. And it is at a pressure of 713 torr, which is the typical atmospheric pressure that you see in Frostburg. And it's at room temperature, which is about 25 degrees Celsius. And I ask you, how many moles of gas do you have in that flask? Now, your first impulse before you knew about this equation would be to go for the grams there and say, I can turn grams to moles. But what do you need for that? You need a molar mass, and I didn't give you one. and I'm not going to. You don't need to get moles from the mass here. You've got enough information here to calculate moles. If you take a look at your gas law, moles in there. If you solve the gas law for moles, you're going to divide both sides of this equation by RT. Now we have to put the units in. And what units am I going to use? Well, I know I can turn torr into atmospheres fairly easy. This was a unit conversion that you did need to know. It's just used so often that you've got to memorize it. So if somebody gives me torr, I'm going to change it into atmospheres. And it is pretty easy for me to turn milliliters into liters. So what I'm going to do is, before I plug them in for P and V, I'm going to turn this into atmospheres. And I'm going to turn this into liters. And then I can use liters and atmospheres and use this value for R. Okay, let's figure out how many liters we've got there. Well, we've got 259 milliliters. And I know that 1 milliliter is 10 to the minus 3 liters. So what I really have there is 0.259 liters if I do the math. And if I go ahead and figure out how many atmospheres I have, I've got 713 torr, and there are 760 torr in 1 atmosphere. So if I divide 713 by 760, I'm going to get whatever the pressure is. 0.93, something like that. Now, I can plug whatever I get for that in for P, plug this in for V. What about the temperature? Now, the temperature's got to be in Kelvin, and I can turn a Celsius temperature into a Kelvin temperature by adding 273.15 to it. So I'm going to have something like 298.15 Kelvin, and I'll plug that in for the temperature. And now, since I'm using liters and atmospheres for my pressure, I can use this value here for the R. Now plug all that stuff in. Put the numbers in for PV, R, and T and calculate it. Don't forget, if you're going to punch it into your calculator, you'll punch it in as P times V divided by R divided by the temperature. All right, so that's a very common and very easy problem to do, and you've got one of those on your worksheet. Here is a variation that uses PV equals nRT, but it involves before and after some change. Before a change, you have one set of conditions, P, V, T, and N. And after, you have a different set of conditions. So let's suppose I've got a little air bubble, and it's deep under the ocean. It's at a place where the pressure is 2 atmospheres. The temperature is maybe 15 degrees Celsius. And the volume of the bubble is, let's say, 10 milliliters. Now, the bubble rises, and it comes up to the surface, and it bursts. And I want to know, what's the volume at this point where the bubble bursts? I'm going to say the temperature at the surface is 25 degrees Celsius, and the pressure at the surface is 1 atmosphere. So I want to know what the volume is after the bubble rises. Now, what I'll do is label the conditions. these are the conditions before the change occurred, and these are the conditions after. So how about if I put a 1 on things before and a 2 on things after? Now I can put these things into my table. The pressure before was 2.00 atmospheres. And the temperature before is going to be, I'm going to put it in Kelvin. So it's going to be something like what? 288.15? And the volume before was 10 milliliters. Now, I know that if I'm using atmospheres for my pressure, it's going to be easier for me to do calculations if I put liters here. And I can do that, but let's try this. I'll just put the 10 milliliters in there just the way it is and see where this goes. Now, I don't know how many moles were in this bubble. I could figure it out just the way we did the last example. I could say N1 is P1 V1 over R T1, and I could figure out what the number that should go there is. But I'm going to just put instead, it's that. Why? Why don't I figure the number out and plug it in there? Well, it's more work than I have to do, it turns out, because if I look at this problem, the number of moles of gas that is in here, I don't know what it is right now, but it's the same before and after. So when things are the same before and after, I'm going to just write the name of the variable there, and I'll just make it the same in both places. So it's the same before and after, and I don't know what it is. I could find it if I wanted to. It'll turn out I won't need to. Now let's fill in the rest. The second volume is the one I'm trying to find. The second temperature, if I add 273.15 to this, is 298.15 K. And the second pressure is 1.00 atmospheres. Now what I would like to do is figure out how to take this data that I have organized in this table and turn it into a formula for the second volume. What I'm going to do is apply PV equals nRT to each row. So I know P1 times V1 is going to be N times R times T1. And I know P2 times V2 is going to be N R times T2, where the N is the same again in both places. And the R, of course, is going to be the same. So step 1 was build this table. Step 2 is set up 2 equations. Step 3 is let's turn these 2 equations into 1 equation. How? It's pretty easy. All we have to do is divide this equation by this equation. P1 times V1 divided by P2 times V2 equals nRT1. nRT2. So I divide the top equation by the bottom equation. Now look what happens. That's going to simplify a little bit. N and R and N and R are the same in the numerator and the denominator. So they're going to cancel out. So this equation with that canceled out is my master equation for solving this problem. I'm going to take that master equation and I'm going to solve for my unknown. Okay, and my unknown is V2. That's the thing that I'm trying to find. So how can I solve for that? I have to get it all by itself on one side. That's what you do when you're solving an equation. So if I multiply both sides of this by V2, I'll do this step by step so you can see my logic. I multiplied both sides of this equation by V2 and I got this. Now let's get rid of the T2. I can move it over to the other side by multiplying both sides by T2. Now let's get rid of the T1. I want the V2 all by itself, so what I'm going to do is divide both sides by T1. And now I have it. I have solved this equation for my unknown. Now all I have to do is plug the numbers in and grind out the answer. Let's do that over here. V2 is going to be, let's see, T2, 298.15 over T1 and now I've got times P1 over P2. Let's see, P1 is 2 and P2, the after, is this. Okay, and what else have I got? B times V1, 10 milliliters. Okay, now look at what the units do, and you can tell you did your algebra right, because this and this cancel, this and this cancel, and my final answer is going to be in milliliters. It's a volume, so that looks right. So you'll always be able to tell if you did this step wrong, because I should be getting volume units that don't cancel, and I do. If you get some other units, that means you did your algebra wrong. So without picking a calculator, can I decide about how big it's going to be? Maybe. This is just a little bit bigger than 1. 298 divided by 288. If it was 288 divided by 288, it'd be 1, and it's a little bit more than that. And then this is going to be 2, obviously. 2 times 10 is 20 milliliters. So I'm going to expect to get something a little bit bigger than 20 milliliters here. You try it. Put it into your calculator and see what you get. You'll probably get something a little bit bigger than 20 milliliters. Now, there's one like this on your worksheet too. And we're going to do some more of these in the next worksheet and explore some special cases that you get from this in worksheet 7.2.